Hey everybody, welcome back. Today we're going to be talking about exponential word problems. So we're going to be taking our growth and decay factor formula that we learned last week. So remember that formula looks like this. There we go. Y equals A times 1 plus or minus, depending on if it's growth or decay, R raised to the power of X. And the reason we're going to use this formula is because we're going to be given how something, depending on the problem, is increasing or decreasing. So there could be some percent increase or some percent decrease, and that percent increase or decrease represents our growth factor. So just to give you a little idea as far as what we're going to be looking for when we tackle these word problems, A represents our initial value or starting point. R is the growth or decay factor. Now again, this is going to be given to us as a percentage. So we're going to take this percent and we're going to turn it into a decimal to represent our R value. So we're actually going to be working backwards from what we were doing last week. And then last but not least, X represents time. So some sort of time that has passed based on the problem. Okay, let's get started. So a construction company purchased some equipment costing $300,000. The value of the equipment depreciates at a rate of 14% per year. So what this problem is saying is the equipment that the construction company that the construction company bought over time ends up going down in value. So if they were to try and sell the equipment after a couple of years of owning it and using it, they probably won't be getting as much money for it as they paid. So they probably won't be getting that $300,000 for it. It'll actually be worth a lot less. So to write an equation of really what the value of this equipment will be after a certain amount of time, this would be an exponential equation. So in looking at our information here, this $300,000 is our initial value. The value of the equipment depreciates. So this is really good to keep in mind because we're going to have a decay factor here, not a growth factor. The rate is 14%, and remember, we're going to turn that into a decimal, and it's per year. That's our time frame. All right, so for part A, where we're going to write a formula that models the value of the equipment, I'm going to just first write down all this information. So my A value, my starting value is $300,000. My R value, in this case, my decay factor, it's 14%, but I'm going to turn that into a decimal. So 14% divided by 100 gives me 0.14. Okay, or you can think about it as you move the decimal place 2 to the left when you're dealing with a percent, changing that to a decimal. And then last but not least, our time, or our X, is number of years. So we don't have a specific value of that. It all depends on what they want us to look for. Okay, so our equation, y equals, and this is going to be a decay factor, so just writing this out, 1 minus r is going to represent our b value here since it's a decay. So now filling in all those pieces, I get 300,000 times 1 minus 0.14 raised to the power of x. And I'm going to simplify this a little bit. I'm actually going to subtract 1 minus 0.14, and I get 0.86 raised to the power of x. So here's our formula that models the value of the equipment after a certain number of years. So to go to part B, what is the value of the equipment after 9 years? So this means I'm going to plug in an x value of 9. So going ahead and doing that, raised to the power of 9. I'm going to go ahead and plug this into my calculator. And when I do, I'll show you everything I get so far. So I get y equals 77. Again, I'm just going to show you kind of everything that comes up on my calculator here. 0.22519. All right, so now since we're talking about money, we're going to cut this decimal place down to the nearest hundredth. So we're going to say the value, or y, is approximately $77,198.23. So that's what the value of the equipment's going to be after 9 years. So you'll notice it obviously has gone down. Originally, they paid $300,000 for it. Now it's only worth $77,198.23. Okay, so let's keep going. The number of newly reported cases of HIV in thousands in the United States from 2000 to 2010 can be modeled by the following formula. F of t equals 41 times 0.9842 raised to the power of t. So remember that f of t represents function notation, so don't be nervous about it. F of t is just saying the function of t. So based on a certain t value, here's what we're going to get. T is the number of years after 2000. So that's something to keep in mind when we write this formula. Okay, so we're going to identify the decay factor. So remember, the decay factor is from our B value. So looking at our equation here, our B value would be 0.9842. And if you remember from last week, we find the decay factor by taking 1 minus R. R is actually the decay factor that we're looking for, equals 0.9842. So what did we subtract from 1 to get 0.9842? Oops, sorry about that. Okay, so I'm going to subtract the 0.9842 from both sides. And I'm going to add R to both sides. I'm going to kind of do a double here in my little space. So let's see, these guys cancel, these guys cancel. And I'm left with, that looks like a lot of gobbledygook, sorry about that. R equals 0.0158. So here's our decay factor, and if you think about it, what this means is, if we turn this into a percent, what this is telling us is there is, if we move the decimal point 2 to the right, or multiply by 100, there's a 1.58% decrease in reported cases per year. So just a good way for you to think about what that decay factor is telling us. All right, so we're going to calculate the estimated number of new HIV cases reported in 2004. Because remember, these formulas are really just to give people an idea of what a possible trend could be, what a possible value could be in the future, just so people are prepared. So if we're looking at this reported in 2004, okay, so remember, our t value is the number of years after 2000. So 2004 minus 2000 gives us 4. So we're working with a t value of 4 here because it's 4 years after 2004. So plugging this in for t, so everywhere I see t, I'm going to plug in 4. Raised to the power of 4. Now you can actually type this into your calculator exactly as it looks. Don't worry about the left side. Remember, the left side is the same as saying y equals. Okay, so we're not going to touch the left side. It's not going to influence our equation at all. So I'm just going to type in 41, parentheses, 0.9842, close the parentheses, raised to the power of 4. And our calculator should be able to work order of operations from that. So going ahead and doing that, I get, and I'm just going to tell you, I'm going to write down everything that I get at first, and then we can shorten this up a little bit. So I get 38.4695671 Oh my goodness. Okay. Now, since we're talking about population, so we're talking about number of cases here, and this is technically in the thousands. So we're looking at like this number, if we multiply it by 1,000, we're talking 38,469. So it's a pretty large number. And we don't want to discount the fact that there is well over 38,000 cases. We're actually almost halfway to 39,000 cases. So what we're going to do is we're going to round this up. And the reason we're going to do that is because we don't want to forget about the 0.4695671 cases. We want to make sure that those are also included in our estimate of how many new HIV cases could be reported. And again, if the government or if healthcare was trying to use this number, you want them to be over-prepared than under-prepared. So it's almost better to look at more cases or at least plan for more cases, even if less could possibly come in. So in this case, we're just going to round, we'll say approximately 39. And remember, this is in thousands, so we're talking 39,000 cases reported in 2004, and that's the number of new cases. All right, so let's keep going. Okay, so for all my March Madness fans here, 64 teams participate in a basketball tournament in which half the teams are eliminated after each round of play. First thing we're going to do is we're going to write a formula to model the number of teams remaining after any given round of play. All right, so we need to find all those key pieces once again. So the first thing, I see 64 teams participated. That's my A, my starting value or my initial value. Half the teams are eliminated. Okay, so when we talk about half, we're talking about 50% of the teams being eliminated each round. Now, eliminated, don't forget, tells us this is a decay. The number of teams are going to be going down with each additional round. Now, that 50% represents our R value. We're going to turn that into a decimal. So moving my decimal place 2 to the left or dividing it by 100 gives me 0.5. And then finally, after each round of play, so round of play represents my time, that's my X. So this is going to be number of rounds. So it depends on how many rounds have passed. That's when we can tell how many teams are remaining. So our formula or our equation, you know what, let's do function notation this time. We'll practice. We'll say f of x equals A, which is 64, times 1 minus, because again, it's a decay, 0.5 raised to x. Okay, so I just did function notation this time just to practice. And then again, just simplifying this a little bit. I get 64 times 0.5 raised to the power of x. Whoop, there we go. Alrighty, so now let's apply this formula. How many teams remain after after 3 rounds? All right, so this 3 rounds right here tells us that x is 3. So let's go ahead and plug that in. So f of 3 equals 64 times 0.5 raised to the power of 3. And again, ignoring the left side, just go ahead and type this into your calculator exactly as you see it. 64, parentheses, 0.50, close the parentheses, raised to the power of 3. So how many teams will remain after 3 rounds? We get 8 teams. All right. So how many rounds of play will it take to determine which teams win the tournament? Now, we could make a table ourselves. We can actually use our calculator to do the same thing. So if I were to if I were to make a table, all right, so let's see if we can do this kind of on our own here. So remember, to win the tournament, we need to get down to one team. We need to get a y value, or in our case, sorry, an f of x value of 1. Okay, so we need f of x to equal 1. Okay, so when we first start, when x is 0, after 0 rounds have been played, we have 64 teams. After 1 round, cut this number in half, we get 32. After 2 rounds, cut this number in half, we get 16. After 3 rounds, cut this number in half, we get 8. And I'm just going to keep going for a second. After 4 rounds, cut that number in half, we get 4. After 5 rounds, cut that number in half, we get 2. After 6 rounds, cut that number in half, we get 1. Ooh. So it looks like after 6 rounds, our team's going to win the tournament. Now, we could also look at our calculator for the same information. So if you wanted, you could have graphed this function. So I could go to my calculator, I can graph 64 times 0.5 raised to the power of x, and I can look at the table, and I can look to see where our y value, or f of x value, is 1. And then the corresponding x value that goes with that, which would have been 6, is our answer. And what you can do is you can actually show this. So on future Regents exams, you can actually show this. So it shows that you used your calculator. The question doesn't necessarily say that we have to do the work by hand. So you would show your table. You would kind of show what you're looking at, and then you would write down your final answer. So that's just something that you could do as well when it comes to the Regents in the future. All right, Cyan bought a used car for $8,000. He boasted that he got a great deal since the value of the car 2 years ago, when it was new, was $15,000. His friend Jack was skeptical, stating that the value of a car typically depreciates about 25% per year. So Cyan got a bad deal. Use Jack's logic to write a formula for the value of Cyan's car. Use T for the total age of the car in years. Okay, so let's think about those key pieces that we need. We need a starting value. So the starting value is how much the car was worth when it was new. So when it was new, it was worth $15,000. So our A value is $15,000. All right, our decay factor here. And I say decay factor because our car is depreciating in value. It's going down. So our decay factor is 25%. Turning that into a decimal gives me 0.25. And then our time frame here, they want us to represent number of years with T. So we'll say T is number of years. All right, so our equation, remember, it has to have a decay factor in it. So we could say y equals, I'll just give you the general layout first. Y equals A times 1 minus R raised to the power of T. And filling in all of the key pieces that we need. A is 15,000, R is 0.25, and we're raising to the power of T. Simplifying this a little bit, 15,000 times 0.75 raised to the power of T. Okay, so here's our general formula. So depending on how many years since that car got on the road, we could see what its current value is. So who's right, Cyan or Jack? So Cyan said the car is 2 years old. So if I plug in a T value of 2, let's see what the car should be worth since it's been depreciating in value. So y equals 15,000 times 0.75 raised to 2. Okay. So going ahead and plugging this into my calculator, again, exactly as it looks, 15,000, parentheses 0.75, close the parentheses, raised to the power of 2. It looks like the car after 2 years will be worth $8,437.50. So I would say Cyan got a pretty good deal because the car is actually worth more than what he paid for it. So in this case, who was right, Cyan or Jack? Well, Cyan is right because he only paid $8,000 when the car was actually worth $8,437.50. So he got a little bit of a bargain. He did not have to pay that extra $437.50. So I would say Cyan is correct. So I'm going to say, to answer the question, Cyan, because he paid less than the car is worth, which is good. If he paid more, if he paid $9,000, he paid more than the car was actually worth. So that would not be a very good deal. But in this case, yep, he saved a little bit of money, so he definitely got the better end of the deal on this one.
All right, now let's take a look at question number 5. So question number 5 says the table below represents the population of the U.S. in millions for the specified years. So in the year 1800, the population in the U.S. was 5 million. In 1900, it was 76 million. In 2000, it was 282 million. So let's take a look at part A. If we use the data from 1800 to 2000 to create an exponential equation representing the population, we generate the following formula for the sequence where f of t represents the U.S. population and t represents the number of years after 1800. Okay, so just underlining some key things here. F of t is the U.S. population, and t is the number of years after 1800. So this is something to keep in mind. Okay, so this is function notation. Here is the formula to represent how our population is increasing over time. We use an exponential function here because you'll notice there's not a constant change. So although our years go up by 100, our population does not increase at the same rate every single time. So we're fitting an exponential formula to this information or to this data because there isn't a constant rate of change. So looking at this, we're going to use this formula that was provided for us in Part A to determine the population of the U.S. in the year 2010. All right, so if we think about that, the year 2010, we need to come up with a t value that we're going to plug in. Now, t represents the number of years after 1800. So to figure out t, now many of you can do this in your head, which is absolutely fine. I'm just showing you what we need to do to get t. I'm going to take 2010 and subtract 1800. So how many years in between? 210. So our t value is 210. So let's go ahead and plug that into our formula. Everywhere I see t, so f of 210 equals 5 times 1.0204 raised to the power of 210. So everywhere I saw a t, I put in 210 years. Okay, going to our calculators and plugging in the right side only. Do not touch the left side. The right side, 5 times 1.0204 raised to the power of 210. So this gives me, I'm going to give you the full decimal that I see on my calculator first. So this gives me 347.3477751. Now, looking at this, so if we were to interpret this number, we're saying that the population in 2010, based on this formula, would be around 347 million people. So 347 million, it looks like about 347,751. So what we're going to do here is we're going to take all of our decimals because we are going to get some decimal answers. I'm going to round to probably the nearest, we'll do 10,000. So we'll do 4 decimal places. Okay, so just to give us a pretty clear picture of what the population is going to be, but still cutting our number just a little bit, making it easier to read. So we'll stop it there. And again, this is millions of people. So about 347.3478 million people. So that's going to be the population, or the predicted population, if we were to use the function that was provided for us in Part A. So now moving on to Part B, it says if we use the data from 1900 to 2000 to create an exponential formula that models the population, we generate the following, where f of t, once again, represents the U.S. population, and t represents the number of years after 1900. Okay, so this one's a little different. T now represents the number of years after 1900. So we're actually not using the data from the year 1800 at all when it comes to this particular function. We're only focusing on the data from the year 1900 and 2000. And here is the function that is produced. So now we're going to use this formula to once again determine the population of the US in the year 2010. Now our t value in this case is the number of years after 1900. So similar to what we did above, we're going to take 2010 and subtract 1900, and we're going to see how many years we have in between. So 2010 minus 1900 gives us 110, and that's our t value. Okay? So plugging this now into our new formula that was given to us, everywhere I see a t, I'm going to put in 110. Again, this is function notation. Don't touch the left side. Multiply the right side out. So 76 times parentheses 1.013 raised to the power of 110. Don't forget to close that parentheses and then raise to the power of 110. And again, I'm going to write down the full decimal that I get, and then we'll round to the nearest 10,000ths place. Okay, so that's the full decimal that I get. Okay, so rounding to the nearest, so we'll do 4 decimal places again. So if I go out 4 decimal places, again, just to give me a really clear picture, and actually I apologize, so I should do, let me change these 2 to approximately since we're rounding. So in 110 years, or in the year 2010, according to this particular function, we can expect the population to be about 314 million people. So 314,680,001.5. So just writing this out, so 314.6680 million people. And you know what? Let's do this. And I'll add it to the one above too. We'll say approximately, since we rounded. Okay. All right, so now let's look at C. The actual U.S. population in the year 2010 was 309 million. Which of the above formulas better models the U.S. population for the entire span of 1800 to 2010, and why? Well, if I'm looking at A and B, I see that the formula, or the prediction that we came up with in Part B, is closer to the actual population than what we predicted in Part A. So I'm going to go ahead and I'm going to say the formula in B, since now we have to say our y. So I choose the formula in B. I think that's going to best model the U.S. population for the entire span. And why? Well, since the predicted population is closest to the actual population. Okay. So what was predicted in Part B is the closest to what the actual population value ended up being in the year 2010, which is why we would probably go with that formula as a best model for predicting population. All right, moving on to D. So we're going to complete this table below, and we're going to project some figures for the years indicated. We're going to be using the formula from Part B to determine the numbers. So now we're just going a little further into the future. We're looking at the year 2020 and 2050 and 2080. Now, because we are using the formula from Part B, I'm going to put that up here really quickly. So just as my reminder, so f of t equals, this was the formula from Part B, 76 times 1.013 raised to the power of t. And again, one more reminder for ourselves. In this formula, t represents the number of years since 1900. Okay, so if we're looking at the year 2020, this would give us a t value of 120, because 2020 is 120 years past or since the year 1900. 2050 is 150. 2080 is 180. So these are the t values that we're going to be plugging into this equation or this function to help us figure out or predict the US population in millions for these particular years. And we're going to round to 4 decimal places once again, just to get a pretty accurate view of what the population is going to be, or I should say that we're predicting the population is going to be based on that function. Okay, so starting with 2020, 76 times 1.013 in parentheses, raised to the power of 120 gives us 358.0528. Okay, again, I'm going out 4 decimal places here. All right, doing the same thing for the next one, 76 times parentheses 1.013, close that parentheses, raised to the power of 150. That gives us 527.5096. All right, and then last but not least, looking at 180, plugging that into my calculator, 76 times parentheses 1.013, close the parentheses, raised to the power of 180, we get 777. Oh, this one's kind of interesting. So with this one, we'll go, if we went out 4 decimal places, we'll go 1659. There we go. Okay. All right, so this gives us a pretty good idea, a nice clear picture of about what the population might be if we were to use that formula from Part B. Now, let's answer Part E. Are the population figures you computed reasonable? And what other factors need to be considered when projecting population? Now, although this worked, obviously, from our jump from 1900 to 2010, this model definitely worked. Is this something that we feel is accurate, and if we were to continue for many years after that? Now, I'm looking at this, and I have to say, in my opinion, I don't necessarily feel these population figures are reasonable, and here's my reason for that. There are other factors that needed to be taken into consideration when it comes to population. For example, we have no idea what the death rate is. We have no idea what the birth rate is. These are 2 things that affect our population. We don't know what's going on in the world, right? Who would have predicted a pandemic like this would be going on that will obviously have an impact on our population as well over time. So while these things seem like they are reasonable values, we are forgetting that there are other factors that do play into population. So I'm going to say no. And the reason for that is we must take into consideration death rate, birth rate, and what's going on in the world. Oop, not and. Okay. And if those factors weren't taken into consideration, then yes, that, these would be some realistic predictions, but unfortunately we do have to take into consideration all of these factors that aren't necessarily included when we calculated our populations, or when we predicted the populations for those future years. Okay. Number 6, last but not least, the population of the country of Oz was 600,000 in the year 2010. The population is expected to grow by a factor of 5% annually. The annual food supply of Oz is currently sufficient for a population of 700,000 people and is increasing at a rate which will supply food for an additional 10,000 people per year. Okay, lots of information here. So we have information regarding population and we have information regarding food supply. So we have to make sure that we keep them separated when we start putting our information down. So the first thing we're going to do is we're going to write a formula to model the population of Oz. Okay, so let's pick out all the information. I'm going to put this in blue that goes along with the population of Oz. So first thing is, it was 600,000 people in the year 2010. The population is expected to grow by a factor of 5% annually. So annually means yearly. The rest of this talks about food supply. So I'm going to stop right here. So what are my key pieces? My starting value, 600,000. And that's in 2010. So just to keep in mind. Okay. Our rate, our growth factor here is 5% annually. We're going to put that in decimal form, so that's 0.05. And our X is number of years since 2010. Okay, because 2010 is where we start, that's where our initial value is from, and then everything past that is going to be our X value, 1 year past, 2 years past, etc. So writing our equation here, this is definitely, this is an exponential. So just to answer this second half of the question, it says, is your formula linear or exponential? It is exponential, and the reason for that is there is a percent growth. Notice how it didn't talk about a constant change. Our population of Oz wasn't increasing by 5,000 every single year. It's increasing by a certain percentage of the total, and that total is going to change from year to year, which means the percentage of people that it's growing by is also going to change year to year. So this is exponential. It is not linear. So writing our equation, remember it is a growth function. So we have, and you know what, actually I'm going to use function notation here because we're going to have two different functions that we're working with. I'm going to call this f of x. So f of x equals 600,000 times 1 plus 0.05 raised to the power of x. Now combining, or just really simplifying this a little bit, I get 1.05 raised to the power of x. And here is my function. Okay. All right, so now we're going to write a formula to model the food supply. So this is going to be the second half of our word problem here. And we're going to decide, is this formula linear or exponential? So the food supply of Oz is currently sufficient for a population of 700,000 people, and it's increasing at a rate which will supply food for an additional 10,000 people per year. Okay, so every year the food supply will increase by 10,000. That is a constant rate of change, which means this is a linear formula. Now we've got to think of linear functions. What are the two key pieces we need for a linear function? We need the slope. So what is the change? What's the average rate of change? And we need the b. What are we starting at here? So our slope is 10,000 because it's 10,000 people per year. And our y-intercept, where are we starting? We're starting at 700,000 people. All right, so writing our equation, instead of y, I'm going to use g of x. So I'm just using function notation, but I'm trying to make sure that I separate our two different functions that we're working with here. So that's why I chose g of x and f of x. So g of x equals my slope, which is 10,000, times x plus 700,000. And here is my formula to model what's happening with the food supply in Oz. So we have a formula to represent what's happening to the population and a formula to represent what happens to the food supply. So at what point does the population exceed the food supply? So when we say this, we're looking at what point does the population end up greater than the food supply. So in our case here, remember f of x represents population. So I'm looking at when f of x ends up greater than g of x. Now we could do this by hand, or we can go to our calculator. So I'm actually going to plug into my calculator right now. I'm going to do both functions, and I'm going to take a look at each of their tables. So remember, if you're using your NSpire to put two different functions or to graph two different functions, you could graph them both on the same coordinate plane. You just hit the tab key. So you'll insert one function, and then you'll hit tab, and then you'll insert the second function. Okay, so let's go ahead and do that. So take a second, graph in your calculator, and you can actually take a look. You can see how our population is an exponential function, an exponential growth. You can see that curve increasing from left to right. You can look at the population linear function, this nice straight line that is also increasing because it has a positive slope. Okay. And I'm actually going to take a look at the table that represents both of these functions. So if we go to the table, okay, so if you go to your table, what I'm going to do is I'm going to start looking, so just to make sense of what I'm seeing on my table here, x represents number of years since 2000. So if I'm looking at an x value of 0, this is in the year, the year since 2010. So if I'm looking at an x value of 0, this is the year 2010. Negative x values we will not be using in this case. We're starting at 2010, so we're starting at an x value of 0. When x is 1, that's 2011. When x is 2, that's 2012. And you can see how your y values are changing with respect to our years increasing. So as our years go up, so as we move further past 2010, our y values are both increasing as well. So taking a look, I'm comparing the y values, and I want to see, when does my f of x function, or my exponential function, become larger than my linear function? And I see that when x is 5, that is when my exponential function is larger than my linear function. In here, I'm just going to show you kind of what I'm looking at on my table here. So when x is 5, so sorry, instead of y, let's do this. This would be my f of x function, that's my exponential, and this is going to be my g of x. So I see this, 5, 7, 6, 9, and 75, and 4 zeros. Okay. So this is the first time I'm seeing that my exponential function is larger than my linear function. So at what point does the population exceed the food supply? After 5 years. So this would be, so after 5 years, so that would be in 2015. Okay. And our table kind of shows for us that justification. So the population will be 765,769, but the food supply will only be able to feed 750,000 people. So looking at D, if Oz doubled its current food supply, so if instead of starting with 700,000, let's say we started with 1.4 million, but we kept it as a linear function. So we're still increasing by 10,000 every year. So our equation, we're changing our B value here. So instead we're going to work with a B value of 1.4 million. So I'm going to write that out. But our M stays the same. Our food supply increases by 10,000 every year. So that gives us now an equation. So our g of x changes to 10,000 x, but now it's plus 1.4 million, so 1,400,000. There we go. So there's our new function. Okay. Would a shortage still take place? Okay, well, same thing. Let's go back to our calculator. I'm going to change now my g of x function. So instead of having the g of x function that I had put in there originally, I'm going to change it and I'm going to put this new one in. So 10,000x plus 1,400,000. And I'm going to look at the tables once again and compare. When are we going to have a shortage? Will they have a shortage with this change? So once again, I'm going to kind of scroll down and I'm going to see, is there ever a point in time where my exponential function surpasses my linear function? So as I scroll and scroll and scroll and scroll, oh, I see it. It does. It is going to pass. So I don't know about you guys, but I'm looking at an x value of 21. So 21 years after 2010, the population is going to surpass the food supply. So yes, after 21 years, the food shortage will happen. And if we think about it, so 21 years. Okay, so 21 years past 2010, so we're looking at about the year 2031 is when this food shortage would occur based on our information. All right, so last but not least, if Oz doubles both its beginning food supply and doubles the rate at which the food supply increases, so now we're changing both values here. So our food supply, we're going to start at 1.4 million, and now instead of adding 10,000 every year, we're going to double that. We're going to add 20,000 every year. So we're going to keep this as a linear function. Our B and our M are going to change. Okay. Why are we not working here? There we go. Sorry, my screen stopped working for a second. Okay, so now we're going to take a look. Hang on, technical difficulties.
Okay, so last but not least, part E. If Oz doubles both its beginning food supply and doubles the rate at which the food supply increases, would food shortages still take place? Explain. Okay, so now our B value is going to remain at 1.4 million, but our slope is going to double as well. So instead of increasing by 10,000 each year, we're going to increase by 20,000. So that creates, once again, a new g of x function for us. And our g of x function is going to now be 20,000x plus 1,400,000. 400,000. So we're keeping g of x, or how our food supply for Oz is, we're keeping that as a linear function. We're just adjusting the slope and the y-intercept to see if that will take into consideration, or if that will change when a shortage could potentially occur, and if a shortage could potentially occur. So once again, let's go back to our calculator. I'm going to take that g of x function. I'm going to adjust it one last time. Now I'm going to put down, so just changing it really quickly, I'm going to put 20,000x plus 1.4 million. And I'm going to look at my tables once again, and I'm going to see, is there a point when my population is greater than the food supply? Because remember, if the population gets greater than the food supply, we're going to have, or I should say Oz is going to have a bit of a problem. So looking at my table, uh-oh, a shortage is going to happen. So yes, a shortage is going to happen after 24 years. So remember, that x value of 24 technically means 24 years after the year 2010. So 24 years after the year 2010, we're looking at 2034. Oh, goodness. That's when we're going to have a shortage in Oz. All right, so that's day 1 of word problems. You got 2 more days to go, and we'll see you soon.